Hello everyone, welcome to lesson number 24 for BC Calculus, where we're going to talk about transcendental derivatives and integration. We're going to go ahead and find derivatives for the natural log. We're going to integrate the natural log. We're going to take the derivative of exponentials e to the x and integrating e to the x. So let's go ahead and get started and talk about how to find the derivative of a natural log of base e. And one thing that is actually pretty awesome about finding this derivative is we can actually use implicit differentiation to do this, because you guys learned back in Algebra 2 Pre-Calculus that y equals the natural log of x. This is how I write our function as a log. You could rewrite this exponentially as e to the y equals x. And so let's take the derivative then of e to the y equaling x. Now the only reason that this is not ideal is that you technically haven't learned the derivative of e yet, but I'm going to tell you what it is because it's actually really easy. So the derivative of e to any exponent is going to be e to that exponent times the derivative of the exponent. So the derivative of y is going to be 1 y dx. Sorry, 1 dy dx. And this is going to be equal to the derivative of x is 1. So then if we continue on with this, we can rewrite this derivative, right? Because these are the same thing. So dy over dx will be 1 over e to the y. And we already know that e to the y is 1 over x. Or sorry, e to the y is x. So this is going to be 1 over x. So then I can say that if I want to integrate 1 over x dx, then that's going to give me back the natural log of the absolute value of x. Or the derivative of the natural log of x is going to be equal to 1 over x times the derivative of x. So those are two little formulas that we hopefully learn pretty well. And now the one that some students from AB, they already know this part, but then they may not know how to take the derivative of a log base a of a function. And usually log, if it's not written, it's base 10, but we're going to go ahead and take the derivative now of log base a of x. And we're going to use the change of base formula here, that the log of a, base a x, is equal to the natural log of x over the natural log of a, where a is a constant, right? A is a constant. So if I want to find the derivative of this, then I'm going to find the derivative of my natural log of x over the natural log of a. I could, knowing this is a constant, I don't really have to use the quotient rule, but I'm going to go ahead and use the quotient rule just because I want to. It's going to be the natural log of a, so your denominator, times the derivative of your numerator. Well, we've already learned now that the derivative of the natural log of x is 1 over x. So it's denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Well, the natural log of a is just a number, so that's just going to be 0, all over our denominator squared. All over our denominator squared. Which we get then that this is going to be 1 over x natural log of a. Okay, so again, 1 over x natural log of a is going to be our answer to this problem. So 1 over x times the derivative of the natural log of a. Now, technically, this would also be multiplied by the derivative of whatever x is. All right, so that's also important for us to understand here when we do that problem. So that's how you find the derivative of the natural log of ax. Okay, so we have our two information things right here. We have this one, where again, if we want to take the derivative of the natural log of x, it's just 1 over x times the derivative of x. And one thing I just want to just show you guys with this and this is that this is the same thing. Right, so I can rewrite this actually. Let's do that. So let's rewrite it as 1 over x times the natural log of the derivative of x times 1 over the natural log of a. So they're the same thing. The only difference is now I've got the 1 over the natural log of a. And by the way, a in this case would be e, right? So this is e. So I could essentially go multiply by 1 over the natural log of e, and that's just 1. So they are the same formula. They are the same formula. It's just that this one just ends up becoming 1 because the natural log of e is just 1. So that's an easy way of memorizing that, especially because most people know what the derivative of the natural log of x is. It's 1 over x times the derivative of x. So if we're looking at some of these examples right here, then, and I like this because example 1 and 2, and I'm not going to show every single one of these problems because again, most of this is just simply practice. But for example 1 and 2, I just like these two examples to do this video because you have to do them in two completely different ways. Like for example 2, this is going to be the natural log of x raised, all raised to the 1/2 power. So this one is actually an easier version of this because this is just simply the chain rule. So this derivative in number 2 is going to be 1/2. You're going to leave everything inside the parentheses alone to the negative 1/2 power, to the 1 less power, right? And then you're going to multiply by the derivative of what's inside the parentheses, which is going to be 1 over x. So this answer is going to end up being 1 over 2x square root of the natural log of x. All right, so everything ends up falling into the denominator. Over here, in this one, you are going to take the natural log of some function. Well, the derivative is simply going to be 1 over that function. That's it, 1 over that function times the derivative of what this function is. Well, the derivative of this function is going to be 1 over the square root of x, right? The derivative of x to the 1/2 power is 1 over 2 square root of x. So this is going to end up being 1 over 2x. So looking at the two questions, they're done in two completely different ways. The other thing I just want to say very quickly about what I'm seeing the examples on here. So example number 3, you would absolutely just drop. There's no thought process here. You drop what's the natural log, and then you're going to multiply by the derivative of what you see here. So it's just going to be 2x minus 1. So this is going to be 2x minus 1 all over x squared minus x minus 2. And if you were to try to integrate this, this is going to be your u. Your u is going to be x squared minus x minus 2, and your derivative is sitting right there, which again, you're going to get, if you integrate this, you're going to get 1 over u du, which again, let's just get back to our natural log, right? Because this is going to be the u in our problem. Again, we'll get to this a little bit later on, but just kind of thinking about these kind of problems as we move forward. And then this one right here, we're going to take the derivative, just like we did in example 3. We're going to plop this to the bottom. Right, so 1 over the cosine of x, and then we're going to take the derivative of cosine, which is negative sine, and lo and behold, we get negative sine of x all over cosine of x, and so we get, this is actually negative tangent. Negative tangent of x is what this derivative is. So if I ask you to integrate negative tangent, you're going to get the natural log of cosecant back. Or if I ask you to integrate tangent, you're going to get the natural log of secant back. So it actually works out pretty awesome in that case, where again, your u is going to be the cosine, and then the du would be the negative sine. So you guys can see, based on these two examples, that if I were to integrate this, that's going to be your u, and then this is going to be the du. So then again, you would get back to what's right here. So they actually are working well together as you count them back up. I want to just really quickly look at question number 5, 6, and 7. 5, you would have to use the product rule, right? So that's just a pretty straightforward one for this. So 5, we would go and do x squared, and then we'd multiply by the derivative of the natural log of x plus the natural log of x times 2x. All right, so that's a pretty straightforward one, but just again, remember, we always have to, don't forget about product rule, quotient rule, product rule, quotient rule for these problems. So again, first, derivative of the second plus the second times the derivative of the first. And then you can solve it whenever you want to. This one, all right, so the log base 5 of 7 plus sine x, this is how I always do the problems. I always have, I just drop it. So no matter if it's natural log or log, I always drop it in the bottom. I then always multiply by the derivative of this, because for both a natural log and a log, you actually do the same thing. So the derivative of 7 is 0. The derivative of sine is cosine. And then I have to say, okay, well, this is a log. I have to then go and do 1 over the natural log of 5. Okay? And so this will end up being cosine of x in the top. And then the natural log of 5 is a number. And then, there's really no simplifying for this. Of course, I'm running out of room yet again. So there's our answer. That's our answer. And then question number 7, I love this one so much because you guys are going to learn this integration coming up pretty soon. But we take the derivative of this, what awesome thing happens when we start simplifying it. So product rule again, we're going to do first times the derivative of the second plus the second times the derivative of the first minus the derivative of this, which is the derivative of x is just -1. So if I start simplifying this, I get x times 1 over x is 1. The natural log of x times 1 is the natural log of x minus 1. And we get the natural log of x. So this is going to be the antiderivative. This is going to be equal to the antiderivative of the natural log of x. And when we start doing integration by parts, you guys will see. I will prove this one to you. I'll show you guys how I'm able to integrate the natural log of x dx to get this back. And again, it's by the integration of parts. Okay, so I think that's a good enough stop for this video. I've shown you guys a good amount of examples of how to take these derivatives of these transcendentals, and we'll come back in the next video and continue on with some more stuff, some more calculus, I should say. So I'll see you guys next video.